sometimes it makes a difference. So.
Hello, everyone. Welcome to the Friday section of CS229. So in the first 3 weeks of the course, in the Friday sections, we'll be covering basically a refresher or review of the prerequisites. This week, we'll be going over linear algebra. Linear algebra will be used extensively throughout the course. Both linear algebra and probability will be used. In this session, we'll cover some of the topics that help you maybe refresh the content better, or help you go through the section notes that are available on the website and help you understand them better. So this lecture should not be treated as a replacement for reading those review notes, but rather some of the things that we will go over today will help you read those notes and understand them better. You still need to go through the linear algebra notes if you're rusty about it. Okay, so here's the plan for today. We'll see how much we can cover. So as a basic prerequisite, I'm assuming all of you have seen the basics of linear algebra before, as in seen what a matrix is, seen what a vector is, performed a matrix vector multiplication, sometime in your student life. That's if this is the first time you're seeing what a matrix is or a matrix vector multiplication is, then you'll probably struggle quite a bit. Okay, so we'll also focus on developing visual intuitions of linear algebra in this session. So, at least I personally find it useful to kind of get a visual intuition of what's happening. And this is why I believe linear algebra is probably, of all the branches in mathematics, probably the one that's most intuitive and easy to understand once you kind of get the visual feel of it. Okay, let's jump right in. We'll start with some notation. Right. Oh, by the way, this class is recorded, so if you want to just focus on this rather than taking notes, you can go back to the recording and take your notes again. But feel free to take notes now as well. Notation first. A vector. So a vector, we will denote it as something in Rn. How many of you are familiar with this notation? You know what this means? Okay, great. So this is an n-dimensional real space. So a two-dimensional real space would be like a plane. A three-dimensional would be like the 3D world. And you can generalize that. And we generally write vectors as a column of a list of n numbers. If vector v is in Rn, then v1, v2, vn as a list of n numbers written as a column. And this means this kind of indicates the position of the vector in that space, where each number is the amount you want to go along each dimension, and the set of all these define a vector completely. So you'll also see a matrix. So as a general convention, we will use small letters for vectors. Sometimes I may write an arrow over there to indicate that it's a vector. And a matrix, we generally use capital letters. You can think of matrix as a two-dimension or a collection of vectors which has m rows and n columns, right? So what does this mean? It means this is you can think of it as a grid of numbers, a11 to a1n and am1 through amn. You can interpret this as n column vectors, each of dimension m, or you could also interpret this as m row vectors, each of dimension n. Right? There are some commonly used matrices that you'll keep coming across. One is the identity matrix. You indicate this by in. What this means is it is a matrix where which is n by n, which has ones along the diagonal and zeros everywhere else. Right? Another thing to kind of keep in mind is that even though matrix is two-dimensional, it's not really representing a two-dimensional space. It's really something in m and n dimensions, right? So, but we just write it in a two-dimensional way. Okay, so this is the identity matrix. You can also have a diagonal matrix. Generally, diagonal matrix are denoted as D. That's a common way to denote them. And in this, you have non-zero diagonals and zero everywhere else. These could be so a diagonal matrix only means that the non-diagonals are zeros. The diagonals could be zero or non-zero, but they're generally non-zero. The identity matrix is a diagonal matrix, is a special case of a diagonal matrix where the diagonals are all one. There is something called a symmetric matrix, which means if you take the transpose of a matrix, you get the same matrix again. So what does a transpose mean? Transpose means flipping the rows and columns. So if you have the transpose of A, where A is an m by n, will be A transpose, where you take each column, treat it as a row, take the second column, treat it as a row. Yeah, so this now becomes n by m. For square matrices where m and n are equal, there is an operation called the trace. So trace of a square matrix A is equal to the sum of all the diagonal entries. It's just the sum. It's a pretty simple operation. What does this mean? It is the sum over, where I is the index, A sub I means the element in the ith row and the ith column. Right? So when we write indices for matrices, the first index generally refers to the row number and the second one the column number. Right? So we have vectors, we have matrices. Right? Just by themselves, they're not very interesting unless you can kind of combine them in some way. So we will see how we can combine them. So the first operation we'll be seeing is taking two vectors and defining what we call as an inner product between two vectors. Right? And let V be a vector in Rn. U also be a vector in Rn. Right? They need to be of the same dimension. And the inner product is then defined as V transpose U. It is sometimes also written as U comma V or V comma U with angular brackets on either side and a comma in the middle. These two effectively mean the same. It's just different syntax. They mean exactly the same. Right? And this will be in R. So you take two vectors of the same dimension and combine them to get a real a scalar. Right? And what this actually means, this actually just means for I equals 1 to n, vi ui. So you take two vectors. Let's take two vectors. By a line, I'm representing a vector as a line. So this is a vector. This is a transpose of a vector. So take the first element, multiply them. And then take the second element, multiply them, and sum them all up. That's essentially what's happening here. Right. So with this, there are already some meaning here. Now, whenever take two vectors, any two vectors, take the dot product. If the dot product is positive, then that kind of means they are similar in some sense, right? And if the dot product is negative, that means they are dissimilar in some sense. Now, the magnitude you get could mean anything, and also the vectors themselves can be oriented in any direction. It's defining the relative property between the two. If the dot product between two vectors is positive, then it's somewhat similar, roughly speaking. Right? And if it is 0, then they are orthogonal. Exactly. So what that means is if you take a vector, imagine this is a vector from the origin, and this is another vector. If the angle between them is 90 degrees, then the dot product will always be 0. No matter how they are oriented, if the relative angle is 90 degrees, the dot product is always 0. So similar means they're these two would be kind of give you a positive inner product. This and this will give you a negative, kind of dissimilar in some way. Right. So this is an inner product. A product that an operation you can define over two vectors. There's another operation that you can define. We call it the outer product. Right. Again, this is a vector operation. This is also a vector operation. The difference here is that think of V in R M. This could R M and V in R N. Now these two need not V and U, right? These two need not be the same dimension anymore. And the outer product is represented as VU transpose, which means now you have a V and a U transpose. I kind of find it easy to remember these operations, and I kind of think of straight lines and orient them. A vector is always vertical, a transpose is always horizontal. So VU transpose will give you now a matrix of M by N. What does this mean? It means for every combination of an element in the column vector and an element in the row vector, pick every possible pair, multiply them, and populate the cell which has the appropriate row number and column number. Again, pretty straightforward. And what you get here, this matrix, when you construct a matrix as the outer product of two vectors, it's also called a rank 1 matrix. Right? You can take two pairs of vectors. Here, let's call it x, y. In R, this is in Rn, Rm, and Rn, and UV, again in Rm and Rn. And you can define xy transpose plus UV transpose, right? And now this will give you, so you're basically doing this, xy transpose plus UV transpose, and this will give you the sum of two rank 1 matrices, right? And this is now a rank 2 matrix. One way to think of these rank matrices is to think of each rank 1 matrix as a thin sheet. You take a few rank matrices, add them up, you get like a thicker matrix, and that's kind of a way to kind of think about it. So this will give you a rank 2 matrix. You take two sets of vector pairs, take their outer product, sum them up, you get a rank 2 matrix. Here I'm making an assumption that these vectors are all linearly independent. I'm assuming you know what linearly independent means. It just means that you cannot represent any one of them as a linear combination of the others. Right? So similarly, you can do this for a set of, say, k pairs of vectors. Right? So xi, yi transpose, where each xi and yi are let's say you have k pairs of xy vectors. You can take the sum of k outer products, right? Up to k of them, and this will give you again, an m by n matrix. And what's going to be the rank here? K. It's actually going to be the minimum of m, n, and k. The kind of rationale behind this is that the rank of a matrix can never be greater than either of the dimensions. It's always something that's kind of bounded by either m or n if they're different, and also it can never be greater than the sum of the number of rank 1 matrices you add up. So it's kind of upper bounded by m, n, and k. And of course, if some of them are linearly dependent, then it's going to be something less than this. Here I'm assuming everything's linearly independent. So another thing to kind of note is that if you're given any arbitrary m by n matrix, right, with some numbers filled here, and if you're asked to tell what rank it is, it's nearly impossible. You cannot just look at a matrix and tell what's the rank of it. There's no straightforward way. If it's diagonal, maybe you can, but in general you cannot. There's nothing like you count the number of zeros or number of odd and even. There's no such thing like that. So it's by just looking at a matrix, you cannot tell what its rank is. You'll have to do something more deeper than that. We'll go over that today. Now, this can now be extended to more operations. So we saw how you can take vectors and create matrix out of them. Now, given a matrix and a vector, right? You can multiply a matrix times a vector. Let's say you have an m by n matrix and a vector in Rn. Now, in order to kind of multiply these, you require that the number of columns in the matrix equals to the dimension of the vector. Now, how would you combine these? So you can think of this matrix as m row vectors, each of dimension n. Right? So what you're effectively doing is, so this is like a transposed vector. You take this transposed vector and do an inner product with this column vector, just like this. You have the same thing here, and this gives you one scalar. Do this, you get another scalar. Do this, and what will be the dimension of this? M, exactly. Because we are doing m inner products, it doesn't matter what n was, you get m scalar, so you get a vector in Rm. Right? Another way to interpret this is take the same matrix and same vector, right? M by n, right? Now, instead of interpreting this as m row vectors, think of it as n column vectors, each of dimension in Rm, right? And now, what you're doing is, let me take a few colors so that it's. So take the first element, do a scalar multiple of the first column, right? And take the second element, to multiply the second vector by that number, and so the number of columns should match the dimension of n, so you get a 1-to-1 mapping, and then you just sum them up, right? And this will give you your output vector. So no matter which approach you take, you'll get the same vector, right? So we did vector, vector, matrix, vector. So the obvious last one is a matrix, matrix. So it's kind of useful to have a good intuition of doing, of thinking of matrices as either rows or as columns. In different scenarios, they get the rows and columns have different interpretations, and it just helps you understand the math better, as long as you're kind of flexible in your mind of switching between these two interpretations. So a matrix multiplication. So here we have an m by k times k by n, right? So in order to multiply two vectors, the second dimension, let's call this a in R m by k, and this let's call it B in R K by N. Right? So the first term, the first dimension of the second matrix and the second dimension of the first matrix, these two should agree. Right? These two should be the same. And then with this, you get a matrix of dimension what? M? M and N, exactly. So M and N. So these two need to be the same, and it disappears in the output, whatever it was. Why does it disappear? Again, there are two ways to kind of interpret this. So the first, we'll see, again, the inner product interpretation. Think of them as M rows, each of dimension in Rk, and the second one as N columns, each of dimension in Rk. So now you can perform basically, you can choose any pair of row and column and do an inner product because they're all in Rk, right? And depending on which row and column you choose, you do an inner product, you get a scalar, and you fill in the cell of the corresponding row number and column number, right? So you do basically M times N number of scalar products, and from each one of them you get to fill one cell in this matrix, right? So this is matrix multiplication. You can do the exact same thing, the same matrix, M by K times K by N, right? And this time, instead of interpreting them as rows and columns, we think of them as columns and rows, right? So here we use the inner product interpretation. Now, you can use the outer product interpretation. This time, however, we will go with, we're going to pair them by index number. So this would be blue, this would be red, black, so on. And you define this to be the outer product of the first pair plus the outer product of the second pair, and so on, plus all the K outer products, and this will give you an M by N. Each of these was M by N. Each of them was a rank 1 matrix, and now we kind of sum all these sheets, and you kind of get a higher rank matrix over there. Right? So yeah, this is whether you perform the operations with this algorithm or this algorithm, you're going to get the same answer, no matter which approach you take. And another thing to note is that when you take a matrix A, right, in our M cross N, this need not be square, and you perform the operation A transpose A, which means you take the matrix A, transpose it, which means now this becomes an N cross M, right, and this is still M cross N. Right? Now, when you multiply these two matrices, you see that these two are kind of agreeing. Both of them are M, and it disappears, and you get an N by N matrix. Right? And this is going to be symmetric. Symmetric means a matrix whose transpose is equal to itself. Right? Did I mention? Okay. So symmetric matrices. Matrices are indicated by R M times N, but if it is symmetric, we sometimes denote this as Sn. It means it's a symmetric matrix, and you just have one number because it's square. You could write it as Sn by N, but you could just write it as Sn. Right? Any questions so far? Yeah. Of this one? Yeah, so this would be, the min of M and K. Okay, now this is all good. These are just, we went over operations that, general linear algebra operations. Now, why do we need this for machine learning? Right? So. how is this going to be useful for us? So this is just a sneak peek into the different ways in which we'll be using linear algebra throughout this course. So first one, we probably already saw this in the lecture. This is to just represent data, right? So the input for our machine learning algorithms, what's generally called X, you think of them as a matrix in n, right? M rows and n columns. This generally means we have m examples and n features. It's like feature 1 to feature n, right? Right. And you can do things like you can take this X, do X transpose X, and get a symmetric matrix like what we did there. So you can represent data, and we'll see how this kind of is useful when you're doing things like linear regression. Second, like in probability, where would we use linear algebra and probability? Covariance matrices. So in probability, for a random variable, it generally has like a mean and a variance. If it's a random vector is essentially just a vector where each of these is a random variable, right? If you have a random vector, this will have some kind of a mean and some kind of a covariance. And if it's a random vector, the covariance is generally represented as a matrix, right? And this will be a symmetric matrix as well. So you're going to be working a whole lot with Gaussian covariance matrices and doing all kinds of things with the covariance matrix of probability distributions. So so we're going to be using, it's going to show up here. It's going to show up in, there's going to be some amount of calculus that we're going to be using. For example, in optimization, gradient descent, right? There's optimization uses a lot of calculus. And so why would this show up in calculus? So let's see this. So think of a function, f function from R to R. Does everybody understand this notation? So for those of you who may be seeing this for the first time, if you're a programmer, think of this as like the type signature of a function, right? So what's the input and what's the output? And f is like the name of the function that you're defining. So this means this is a function that takes a real value as an input and outputs a real value, right? So the value here is in R. So what's the type of the first derivative for a function like this? It'll be R. So an example here is, let's give an example, x square. Like x square takes in a number x, returns a number, like squaring it. Both are real values. The first derivative is going to be 2x, which is again a real value. In this case, like the second derivative is also in R. You can also have a function like this from Rn to R, whose value is R. Now, can you think of a function that takes in a vector and returns a scalar? Trace takes in a matrix and returns. So that would take an m by n and return R. Dot product takes two of these. So if the dot product can be represented like this, f from Rn to R. So this would be dot product, where it takes two matrices in Rn and returns R. I'm sorry? Yeah, the norm of a matrix, sure. So if this is a vector, a norm of a vector. So you take a vector, return the norm. There's something more something you've already seen, the cost function, right? So cost function takes in a parameter theta and returns a cost value, right? And what will be the gradient in this case? What the signature of the gradient? What type would it be for the cost function? So the gradient will be in Rn. So this theta will be in Rn. So the gradient in this case will be like a vector that represents the partial derivatives of each of the theta I with respect to the loss. So it will be a vector. Now, what about the second derivative? This is probably the most important one for us. N by n? Yeah, it's going to be an n by n matrix. In fact, it's also going to be a symmetric n by n matrix. Right? And so this is commonly called the gradient. And the second derivative of such a function is called the, anybody? Hessian. Awesome. This can be generalized even further. So f from Rm to Rn. Can anybody think of where such a function might show up in machine learning? Sorry? Yeah, a feature extractor maybe. More commonly, in terms of optimization, we're going to see this as like a layer in a fully connected neural network. If you don't know what this is, don't worry. Right? So let's say the input layer is m dimensions and the first hidden layer is n dimensions, then there's going to be a function that transforms it. And you can take, so the value here is in Rn, and the first derivative will be m by n. So for each of the output, each element in the output vector, take the partials with respect to all the inputs and repeat that for the next output in the output vector, and you'll get a matrix. This is also called the, anybody? Jacobian, exactly. And you can take the second one. This will be something like m cross n cross n or m cross m cross n, whatever. So it's like some kind of a higher order tensor. I mean, that's not very interesting. So yeah, we're going to be using matrices in optimization. Whether it is optimizing a linear regression model, optimizing a logistic regression model, we're going to encounter, we're going to come across the Hessian as well. So kind of linear algebra shows up in multivariate calculus. Another application where we're going to be seeing linear algebra in this course are kernel methods. Right? So in a kernel method, there is something called a kernel matrix. And this is generally in SM, where m by m, where m is generally the number of examples that you have in your training set. In most of the other places, there would be n, but a kernel matrix is generally like a function of the number of examples you have, and each element over here kind of represents some sense of similarity. Are they similar? Is this example similar to this example? And like the similarity value will be here. So that's a kernel matrix, and this is going to be symmetric because distance is symmetric. Yeah, so we're going to be using matrices there as well. Cool. Any questions so far? Yeah.
Can you write a little bit bigger?
A little bit bigger. Okay, I'll.
When you go on.
Sure. Thanks for bringing it up. Any other questions? Cool. Okay, so let's move on to some geometric interpretation of what's actually happening when you take these things. So first thing you want to do is stop thinking of matrices as a set of numbers, but start thinking of them as functions. But what does that mean? A matrix is a set of numbers. How do you think of them as functions, right? So for that, you kind of go back to this view over here, right? Think of let's say A as r m by n. Let's consider a vector x in Rn, and when you multiply A with x, let's say you get a vector B, and B will be in Rm, right? Now, right? So Ax equals B. This is pretty straightforward. A is a matrix multiplied by a vector x in Rn, and you get a vector in B. So you can now think of A as a function, right? If you think of A as a function that takes in a matrix and returns another matrix. It takes in a vector and returns another vector, right? So you can think of A as a function from Rn to Rm. It takes in a vector and returns another vector, right? So this view of thinking of functions as some kind of an operator, of thinking of matrices as some kind of an operator or function is pretty key to kind of getting a good feeling for or intuition for linear algebra. So let's see what this might be doing. So let's see an example of A in this is example A in from R3 to R3, and let's assume A is full rank. Right? So I'm going to use my limited drawing skills to represent a three-dimensional space on a two-dimensional whiteboard here. X, Y, and Z. So think of this as a three-dimensional space. So this is going to be your input space for the function A. It's actually a matrix A, but think of it as a function, input space, right? And you take any point in this three-dimensional input space of A, right? Kind of run it through A, right? And it's going to map it to some point in this output space. Z, X, and Y, right? So for example, take a point over here. I'm going to use some colors over here. Point Z, or some this blue dot over here may get mapped to over here. So you take this vector; it's going to have some coordinates, right? Think of this as X. Oh, there's an X here. Yeah. So let's think of this as P, some point P, and you run it through A, and this will be A of P. Is this clear? Any questions on this? Right. So every point in the space will have a corresponding, will map to some point over here. Let's think of this. Call it Q, and maybe Q gets mapped here, right? So this is A of Q, right? So this basically this mapping from input space to output space is captured by this function or matrix A. So the entire mapping of how every point in this space gets mapped to every point in this space is represented by A, right? And because it's a full rank matrix, every point in the input space gets mapped to a unique point in the output space. If it's full rank, it's also called a bijection. Bijection essentially means there's a one-to-one mapping between every point in the input space and the output space, and no point in either side gets mapped to more than one point on the other, right? Any questions on this? Right. So next we'll see what happens if A is not full rank. Now things start getting interesting if it's not full rank. This is going to be X, Y, Z. Now again in R3. This could be Rn. It's just easy to visualize when it's in 3 or 2 dimensions. And you have A, X, Y, and Z. Now, when it was full rank, there existed a bijection between every point in the input to every point in the output. But let's say it is, say, rank 2. But it's mapping 3-dimensional spaces, but its rank is just 2. This means there exists a two-dimensional subspace. So what does a two-dimensional subspace mean? You can think of a two-dimensional subspace as, for example, this sheet of paper extending infinitely and existing in this three-dimensional world. So this paper would, or this infinitely extended paper is like a two-dimensional subspace in this three-dimensional world, right? So there exists a two-dimensional subspace because its rank is 2. Let's see how I can draw it. So imagine this is like a paper, and it kind of extends indefinitely. And this gets mapped to some other two-dimensional plane in the output space. It could be oriented in a different direction, right? So now a rank 2 matrix is creating a bijection between every point in the subspace to this subspace, even though it superficially is existing in a larger ambient space, right? Now, what does that mean? There is a unique map between, let's say, a point over here in the subspace to here. So if this is P, this is A of P, right? If this is Q, then maybe it's just here, A of Q, right? Now, you got to be careful when, or rather, I have to be careful when I use the word bijection between these two subspaces. What I mean is that when you consider the set of all points that exist on the subspace and the set of all points that exist on this subspace, then there is a bijection. It is absolutely not a bijection between any point in this three-dimensional space with anything over there. Right? It's only a bijection between the subspaces that exist along the matrix rank. Right? What this also means is that any point outside the subspace, right? Let's consider this point over here, right? That point over there. There is no. It's not possible to find any vector in the input space that when you go through A, you will reach this point. So this is inaccessible. Right? This is inaccessible. So it's inaccessible on the output space, right? So there are specific terminology we use. We call this space in the input space as the row space. And this linear subspace as the column space. Now, even though A may be M cross N, the rank of the row space and the rank of the column space will be the same, even though they may be embedded in a different dimensioned ambient space. Right? Now, what does this mean? Because this point is not even accessible by A, it's not possible to have an inverse for this point. Right? So in this case, in the first case, since it was a bijection, A was every point that took something in the input space and mapped it to the output space. The reverse is called A inverse. Right? That takes this as the input and maps it back to output. Now, when you have a lower ranked matrix, an inverse does not exist. Right? Because you have these inaccessible points and there's no way you can map them back here. And also because, as we will see next, the set of all points in the input space that get mapped to AQ are actually an infinite number. Yeah.
Please clarify what you mean by subspace in the context of this one.
Yeah. So a matrix can be of dimension m by n. Right. Now, depending on what rank that matrix is, where think of this as like the rank of the matrix. If you have a lower ranked matrix, even though its dimensions are much higher, there exists a subspace of dimension k, where k is the rank of the matrix. So for example, this sheet that extends indefinitely is a two-dimensional subspace of this three-dimensional world. Right? That's one way to kind of think of subspaces. So even though it takes as input any point in this m-dimensional space, there is actually a subspace for which a bijection exists.
So all the points are within the subspace for the bijection?
Yes, for the bijection, all the points are within the subspace. It can still take any point and map it to some point, but then there's no bijection for that operation, right? So what happens when let's say you take this matrix A and you feed it a point over here, let's call this R, that does not exist in the subspace, right? So you can still perform, AR equal to, and you'll get something over here. Now, what's that going to be, right? This is a perfectly fine operation to do, where you take a point that's not in the subspace. What happens here is that the point R gets projected onto the subspace. Right? What does a projection mean? We'll go we'll go into what projection means in a second. The point R gets projected onto the subspace, and A of projection of R is so the projection would map to some point over here. So any point that projects onto a point on the subspace, they all get mapped to the same point on the other side. Is this clear? If this is not clear, yeah.
How do you know where the row space is?
So the row space is defined by the values of A. So if let's say A is right, it has some numbers. So and now if you take all the rows and take every possible linear combination of these rows, they define your row space. Right? So this is called the row space, which means these are the points, or only those points which can be reached through a linear combination of the rows exist in the row space. Similarly, only those points that can be represented as a linear combination of the columns is the column space. Yep.
So could you try maybe doing like an X, Y, Z? So like if the Z values are just truncated, or
X, Y, Z.
just like the picture that you have, we assume X, Y is the subspace with the two dimensions.
Oh, so
That's not really how you.
yeah. So apologies. So this is not a space that is on X, Y. So it's oriented in some way. Exactly. Every point here has some X component, Y component, Z component.
Okay.
Every point in this subspace, even though it kind of looks like it's like flat on the XY plane, that's just my poor drawing. It's supposed to be some two-dimensional plane oriented in some way. The only condition is that it needs to include the origin. It has to pass through the origin, and yeah.
Isn't that the same rank then, that subspace?
Exactly. It is the same rank, but it could be oriented in a different way, and therefore every point here gets a proper X, Y, and Z value. Right? It has an X, Y, and Z value, but if you take the set of all points that you can reach through the linear combination of columns, it's going to lie in a subspace. Yeah.
Do you have any intuition as to why the row space is, or that subspace at the input is the row space?
Yeah. So it's actually because when you take a matrix and multiply it by some vector, right? You kind of do a dot product with these rows. Now, if it's a low-ranked matrix, then because of the property I mentioned over here, whether the inner product is positive or negative or zero, those vectors that are kind of orthogonal, and any vector that will result in a zero matrix is kind of orthogonal to the subspace. Right? That's like the approximate intuition. Right? Yeah. So in order for a matrix to be invertible, there are like two requirements. One is that it has to be a square matrix, because if it's not a square matrix, then there's no way you can kind of create. There's no possibility of even creating a bijection. Right? It has to be a square matrix, and it has to be full rank. So if a matrix is square and has full rank, then it's an invertible matrix, because you can. A bijection will exist. Now let's go on to this projection deeper. What's happening here? So let me see. right? So what does a projection mean? Let's imagine there is this, there exists a subspace, right? So this is the origin and x, z, y. Again, this subspace does not necessarily lie along the xy plane. It is oriented in some way, but it just has to pass through the origin, right? Now, and now let's consider some arbitrary vector. Let's call it b, right? Now, we want to think of or try to get a better understanding of what happens when you take a vector that's not in a subspace and you project it down. So in order to understand what this projection means, right? So first let's see what does projecting one vector onto another vector mean, right? So let's think of this as a vector b, and let's think of this as a vector v. There are no spaces here. It's just one vector and another vector. What does projecting b onto v mean? It means what is the point along the direction v that is nearest, in some sense, to this point b, right? So would this point be the nearest? Maybe not, because if you move a little closer, this point would probably have a smaller distance. So you can show it that the point that is nearest along v to the point b is one that makes a 90-degree angle, right? Is it clear? Right? So given a vector b and a vector v, right? So the projection of b onto vector v is equal to v transpose over v transpose v times b, right? So what's happening here? Let's see. So this is v transpose. So this would be a rank 1 matrix. V transpose v is the inner product of something itself. So that's going to be a scalar. So this is a rank 1 matrix times a vector, and this will be some vector. Let's call it b hat. Right? So this is the projection of b onto v, right? And this matrix is also called the projection matrix. It's the projection matrix of the vector v. So if you have a vector and you construct this projection matrix, now given any other vector, you multiply it with this matrix and you'll get the projection of that vector onto this. Right? So this is called the projection matrix. Now similarly, you can extend this concept for projection to subspaces. Right? So instead of having a vector v, imagine you have a matrix v where the columns of this matrix represents elements in the subspace that can define the subspace. So if you think of, say, one vector over here, let me call it v1, and another vector v2. So together v1 and v2 can define the subspace of this blue subspace. They can be any two vectors which when you take the linear combination, you can reach any other point in the subspace. So taking any two basis vectors for the subspace, so that's what you mean by a basis. A basis vector are like the atoms, and then you take all linear combination of these and you get an entire subspace. So you can take any two vectors and you could have also taken this and this, in fact, 3 and 4, and that would also be a perfectly fine basis. Right? So in order to project a vector onto a subspace, you need to first construct a basis for that subspace, right? And then create a projection matrix for this basis. And that would look like this. So consider the matrix V, which consists of, say, V1 and V2. Just take any two bases. So if this is a 5-dimensional subspace, then you need any 5 vectors that can make up, that can define a basis for that subspace. So take this matrix V with a set of valid bases and construct a projection matrix onto the subspace. So it's going to look similar to the projection matrix in case of a single vector, except the notation will look like this. So it's going to be V transpose V inverse V transpose, right, times B. Right? So these two, if you kind of look at it carefully, they're somewhat similar. So you have a V times V, and this thing is the inverse, so it's kind of, it goes to the denominator, and you're multiplying them. So this is like the matrix equivalent of this notation. Right? So this is called the projection matrix for the subspace. Subspace defined by V1 and V2, where V1 and V2 are the columns of this matrix. Yeah.
Can you just read the original projection matrix one more time?
So this is, here it's a small v, right? So it's a V transpose divided by V transpose V. So V transpose is the outer product, and this is the inner product. So this gives you a matrix. And this, it's somewhat, it's like the analogy of this one in a matrix space. So the V transpose V, this goes to the denominator. You can think of it as going to the denominator because it's an inverse, and the VV transpose like the VV transpose. Right? So this gives you a projection matrix for projecting any vector onto a subspace. Right? Now, why is this interesting? Because we will now see how you can kind of get a visual interpretation for linear regression that we saw in class earlier this week. So in class we saw linear regression as a process where you minimize the squared error, right, of theta transpose x and y. For each one, you square the difference, that's error, and you sum over all the squared errors for each example, and you do gradient descent to minimize it. And then we also saw a second interpretation using the normal equations. Right? So now we will see why that normal equation kind of makes sense. So you guys probably saw the derivation of how the normal equations was derived with algebra. That was a whole lot of symbol pushing, but it actually has a very nice geometrical interpretation. So let's start with an input space. So I'm going to call this theta in Rn. Right? This is the space of parameters or the weights or the parameters that you train your model, and then you have x. X is your design matrix. The rows and where each row is an example, each column is a feature, right? And this is, I'm going to call it script y, right? Rm. So theta is in Rn, the output space is in Rm, and x is your, the set of features, right? So obviously x is not invertible because m and n, it's not a square matrix, right? So as we saw earlier, there exists a subspace in the space of y's, right, which has this, we'll call it the column space of the matrix X that exists as a subspace in the space of Y that has a dimension of n, where n is the dimension of your input space. So this subspace cannot be bigger than n because your input space is of dimension n. You cannot possibly map it to a space bigger than n. So this is the column space of the matrix X. And to remind, these are your parameters. This is the space of all parameters. This is input, and this is output. Right. So, for example, these are, going back to the example of house prices. These are different houses. These are different features of the house, like the area, the number of bathrooms, etc. And these are so these are what So in the linear regression example, the output was like price of house. It was just a single value. But here we have a space. What does this mean? Right? So this means if you have m examples, each house can get some specific value, and they become like the coordinate values. So a value over here means in your data set, house number 1 had this value, house number 2 had this value, house number 3 had this value. Right? So here, because it's in Rm, each dimension kind of represents one example, right? And each point in the space represents a possible set of values that your data set could have contained. Does it make sense? Right? So this is the space of parameters, the set of all parameters that could possibly exist. This is the matrix that you were given, and this is the space of all y values that your examples could have taken. So your input x exists like a matrix, and the output y, depending on what the y was, is actually just one point in the space. Right? That's the training data you were given. House 1 had so x, y, and z. This is like this has some coordinate values for each x, y, and z, and those are the y values for each example. Right? So this is some point that your entire data set, the y in your data set is represented as one point in the set of all house prices every house could have taken in that space. And now what happens? In order to try to solve x theta equals y, again over here, x, every row is a different example, a different house. Theta is like the parameters you want to calculate, and y is the price of each house in the same order. And we want to find theta in this case. Obviously, this is not invertible because it's x is not a square matrix. So instead, what we want to do is find out the subspace of all the possible house value combinations that can exist for any value of theta, given the set of features that we have. What does that mean? It means for the given given features that you have in your training set, no matter what parameter value you choose, there is a limited subspace for the set of all house values that can exist, for a bijection to exist. So what we do is now, say in your y from your training data might exist at some point over here. Let's say this is the y, or the capital Y, so the set of all house prices exists. And what we want to do is project it onto the subspace that is reachable through your matrix X. Right? So we want to project this onto the column space of X. How does that look like? We do the same thing. So in this case, y is the vector we want to project. The column space onto which we want to project is defined by the columns of V. In this case, it's X. So the projection of y onto the column space of X will look like X transpose X inverse X transpose Y. Right? So this is the projection of the set of house prices onto the column space of your features. Right? And now, once you find the projection, we know that the projected point can be mapped back. Right? As we saw there, there's a bijection between the column space and the row space. Right? So this is the so instead of solving for this, we want to solve x theta equals projection of y onto x. Right? This is not solvable, but this is. Does this make sense? This is solvable precisely because there is a bijection between the row space and the column space. Right? So the theta is in the row space of x. Right? This subspace is the column space of x. Right? And theta can only be mapped to the column space. But in the training set we are given, we get some y values which very likely will not exist on this column space. So we want to project the set of y values onto the column space of x and map it back to the theta, and that's going to be, like the solution of your linear regression. So we cannot do this. So we want to do this instead. Right? We cannot solve this. So project y onto the column space of x and now solve for theta. Right? So what does this look like? So the projection is this one. So we now want to solve x theta equals this. Right? This is what we want to solve. Now I'm just going to reshuffle some. Right? So now you get theta equals x transpose x inverse x transpose y. Right? And that's the normal equations that we found in the lecture. Right? So one way is to kind of go through the algebra and take all the derivatives, set the derivative to 0, and solve for x. You get at that answer. Another way is to kind of think of it geometrically. You have your features over here, where each row is a house. Each column defines, each column is a different feature of the house, right? And then you have a corresponding y, which is the price of each of those houses, right? Now, this is a vector in Rm, so it resides in an Rm dimensional vector wedge. Each house, is like on its own axis. So any point on this Rm defines the set of all house prices in their data set, right? Now, you want to find a theta which will match such that x theta will be equal to y. But that may not always exist because theta is in a smaller dimensional subspace, and there's no reason that theta x will be equal to y. So instead, we want to do something that is reasonable. So what do? We project y onto the subspace that is reachable by theta and x, and then find the inverse of theta. Right? So it's this concept of projection is super useful. Linear regression is one example where we see projection in action. There are lots of other places where a very reasonable thing to do is take a data point, project it onto some space that is manageable, and kind of then invert it. That's a very common pattern. Yep.
If y is already in the column space of x, does that mean the sum of squares is 0?
Yes, exactly. If y is already in the column space, then if you try to minimize the square error, you will you can reach 0 error. Yeah. If y is not going back to the gradient descent approach, let's define your cost function, right? If y is in the column space of x, then the minima will be at 0. So you can reach 0 error if y is in the column space. If y is not in the column space, it's going to be something like this, where this is kind of, the gap is somewhat analogous to this distance. The farther away you are from your column space, the lowest error you can achieve is bigger. This one? So this is x theta equals, so basically the projection matrix times y, and where I redid the brackets. So this is x, parentheses, x transpose x inverse, x transpose, and y. Yeah.
On the point of thinking about matrices like functions,
Yeah.
not like sets of numbers.
Yeah.
Normally, when like thinking of linear regression, for example, I would think of x as the input.
Yeah.
Whereas the way that it's sort of written is like x is the function and theta is the input.
Exactly. Yes.
So how, I don't know, how do you like?
Yeah. So there are two parts. So one is the output of your machine learning algorithm, which will be a model, and for that model, new x is the input, and the predicted house price is the output. But for the learning algorithm, right? For learning algorithm, you kind of think of x as fixed, and you want to find a mapping, the inverse mapping from x and y back to theta, right? That's kind of what you are trying to do. Any questions? Cool. So in the remaining 10 minutes or so, we'll try to do a quick overview of these methods, these topics. So we saw, when you think of a matrix as a function, we saw. So here I'm going to limit myself to 2 dimension, just because drawing things are easier. So think of a matrix in 2 dimension, right? A in R2 cross 2. Right now, every possible input. So let's say a thick line is an input that you feed into it, into A, and the point that it gets mapped to, let me draw it by a dotted line. Right? So let's say this is P, this is A of P. Right? So if this is a full rank matrix, then every point gets maps to some other point. Previously, I was drawing the input space and output space as 2 different plots. Now I'm kind of overlaying them, because in this it's going to be easier for what we're going to do next. Right? So every point P gets mapped to some other point. Now, to kind of get a good feeling for what this might look like overall, one thing that what we can do is imagine a unit circle, right, of radius 1, and see what happens to every point on the circumference where it gets mapped to. Right? That's and kind of the shape and the orientation of the resulting figure, which may not be a circle, kind of summarizes the overall action that your matrix is trying to do. Right? So if we do this, and then let's say the point on red is here, and maybe that gets mapped to a point here. Right? And now if you kind of connect all the output points, you're going to get a figure like this. Right? So this kind of summarizes what the matrix is doing overall. Right? So a space that existed like this is stretched this way a little bit and kind of squeezed this way a little bit. Right? That's like an approximation for something that's just kind of do overall. Now, any given matrix, right? If you think of what a matrix can do, it's limited to a combination of 2 things. It can either rotate your space in some way, or it can stretch or shrink your space in some way. Right? Those are the only 2 things that a matrix can possibly do. Those are like the primitive operations. Now, for any given matrix A, let's limit ourselves to square matrices for now. What it can do can be decomposed into 3 substeps. So you can think of it as doing a rotation number 1, scaling, rotation number 2. So any matrix can be decomposed into 3 steps, right? Yeah. Okay, let me. So this is rotation number 1, scaling, followed by rotation number 2 in this order, right? So in this case, what's happening here? So there was this sphere or a ball. It was rotated. If you kind of imagine the axis of this, it was rotated by some, I don't know, maybe 40 degrees or something, and then scaled by stretching along this direction and shrinking along this direction, and then rotated back. Right? So you can any matrix, any square matrix can be broken down into 3 sub operations, and breaking it down into these 3 operations is generally called decomposition. There are other kinds of decomposition, but this is probably this family is the one that's most interesting. And even here, there are 2 subtypes, right? So one subtype is what's called the eigen decomposition, where you do some kind of a rotation, a pure rotation, right? And followed by scaling, possibly by a complex number, a complex scaling, followed by the inverse of the first rotation. So let's call this rotation 1, and this is rotation inverse. Right? And there's another kind of decomposition called SVD, where you do rotation 1, scaling only by real numbers, and then rotation 2. Right? So what's the difference here? Here the scaling can be either real or complex, but the rotations are the inverses of each other. So you temporarily rotate, it by some way, scale it by a complex number, which actually involves, implicitly could involve rotation, but and then after the end of this step, which may have done some rotation, undo the first step, right? For the singular value decomposition, you rotate it by some amount, but you only scale it by a real value along the dimensions, and then you rotate it a different way. It may not be the inverse of the first rotation, right? These are 2 different kinds of decomposition, which essentially means you're breaking these a big function into 3 sub-functions, which in our language means you're breaking one big matrix into product of 3 matrices. Right? So this will be an orthonormal matrix because it's a rotation matrix. And this will be a diagonal matrix. And this is also going to be another orthonormal matrix. Right? Now, if you take a matrix and decompose it, do the eigen decomposition or you do the singular value decomposition. Now, if the 2 agree, if you get the same set of decomposition in both the eigen decomposition and singular value decomposition, then it has to be a symmetric matrix, right? So symmetric matrices have the same eigen decomposition and singular value decomposition, and symmetric matrices are the matrices that we'll deal most with, right? And the set of all eigenvalues that you get are also called the spectrum. Now, what does this mean? Now, if this were to be the action done by a symmetric matrix, it would mean that there exists, what you might think of as a primary axis and a secondary axis, such that any vector that was along the primary or the secondary axes in the input space will end up having the same direction in the output space. That's because you rotated it, scaled it by some amount, and you rotated it back. And any other vector would have undergone some amount of rotation by the end, but those that were along the primary axis of the ellipse, the amount by which you rotated, will end up being the output will end up being along the same axis. So these axes are called the eigenvectors. And the amount that you scaled, it could be more than 1 or less than 1. And those are the eigenvalues. Right? And the spectrum is the set of all eigenvalues. Right? And we are almost out of time, so I'm going to quickly wrap this up. There are some interesting properties of the spectrum. So the first one is the set of all eigenvalues. The sum of all the eigenvalues is equal to the trace of the matrix, which is also equal to sum of the diagonals. Right? And the last point, the product of all the eigenvalues is equal to determinant, the determinant of the matrix. Right? So this gives kind of a nice interpretation to the determinant. So what's happening here? So you start with some space, right? And the action of the matrix kind of either you can imagine what happens to the volume of the input space and the volume of the output space. Is it increasing or is it decreasing? Right? So the determinant is actually the ratio of the volume of some. So the determinant is equal to the ratio of volume of A of some shape in the input by the volume of the shape in the input. So it kind of, and this shape can be the same, can be anywhere in the input space of any shape, right? So you take some kind of a volume, run it through the matrix, you get a new shape. What's the ratio? Did it increase or did it decrease? That ratio is the determinant. So it kind of gives you a sense of overall, is the matrix increasing the space or decreasing the space? And this is something that you'll actually encounter when you're kind of doing a linear transformation of probability distributions, because we want the overall volume to kind of be equal to 1 of a probability space. So whenever you do a linear transformation of a probability space, you divide it by the determinant. So that's something you'll see down the course as well. And I think we are out of time. Thanks. Yeah.
So when you're doing the projection matrix,
yeah.
xt, x, and
so the projection. This is the projection matrix.
yes.